In this last subsection on binary search trees, I want to talk briefly about balanced binary search trees. And these are a way to get around this problem that the unbalanced search trees had that we've discussed before. Namely that if the insertion order is unfortunate, the height can degenerate to linear, and then all the operations are very slow. I asked you before we got started, what kinds of balanced binary search trees you might already know. And here are various examples, but many of you have said none, which means it's worthwhile spending a little bit of time discussing these. That said, we don't have time to really go into the detail of any of these, but I want to give you a rough flavor, and I want you to be able to use these as a black box in a sense. If you ever need to know more, the lecture videos that I referred to earlier have details about one of these variants. So what is a balanced binary search tree? It is, first of all, it consists of two components. It's a rule how the shape of the tree can look like. And this rule is similar to what we had for heaps. So remember, binary heaps had this very rigid shape where the tree had to be an almost complete binary tree. But it turns out for binary search trees, this is too strict. You cannot really maintain this in a dynamic way if you insert and delete elements at random positions. But you can get something that is slightly similar to this. Shape invariants that are slightly weaker, but still guarantee you that the height is logarithmic in the number of keys. And that's the best you can hope for, as the heaps demonstrated. Heaps, the heap shape, the complete binary tree, is a binary tree of minimal height for that number of keys. So you cannot possibly hope to get better than this. And the second important part is that there are rules that if you insert or delete elements in this tree, that you can maintain this shape invariant. There's many such examples known. The most famous ones are AVL trees and red-black trees. Slightly less well-known, but desirable for some other more specialized properties are the weight balance trees. Because not so many people have seen this, let me point out just the type of shape invariants that these balanced binary search trees have. So for AVL trees, we insist that whenever we have a node which has two subtrees, then one of these subtrees might be smaller, right? And they will have two heights. There's a height of the right subtree and a height of the left subtree. And the AVL condition requires that the left and the right differ by at most 1. So the height of these two trees has to be essentially the same, but we leave a little bit of slack. If you compare that to the heap again, here the height of, if there was a node here, then these two subtrees had exactly the same height. There's only a few nodes where the subtree heights would differ by 1. Now in AVL trees, we allow this for every single node. We allow the height of the left and the right subtree to differ in any possible node. And you can prove that this is still balanced enough to give you a logarithmic height in the worst case, if you can maintain this invariant. So you have to make sure that this invariant is also true when you add new elements to the tree or when you remove elements from the tree. And there's clever rules based on rotations that manage to do this. But I won't give more details on that. A similar idea is red-black trees. It also has some restrictions on how the tree looks like. Here the invariant is slightly more complicated, so maybe I won't go into detail. But there are red edges and black edges, as the name might suggest. And we always have, if you go down a path, you can never have two red edges in a row. So this is not allowed. You can have red edges, but they must at least alternate. You can have as many black edges as you want, but no two red edges in a row. And the second thing is, so that's one condition. And a second condition is all leaves have the same black height. So by black height, I mean, if you start at the root and you walk down the path to this leaf, you only count the black edges and you ignore any red edges. Now, that makes it obvious if you had an arbitrary number of red edges, then this would be not very balanced. But if you have just every other edge is red, then that means the height of two leaves can differ by at most a factor of 2, and it turns out that again is good enough. And this type of trees is introduced in this book and in the videos I referred to. So I'll just say look at Sedgwick and Wayne's book for more details on these. There's a very nice way to motivate them. Why exactly this weird type of invariant, but I won't have time to discuss this in detail today. All right. Let me put that a bit on the side. So these are typical examples of balanced binary search trees that achieve a logarithmic height, and they can maintain this upon updates, again in logarithmic time, which means all operations run in logarithmic time in the worst case. So that's the best you could hope for, and it's this type of trees that are usually implemented in libraries. The Java library has red-black trees. The C++ library, the GNU implementation, has red-black trees. Many programming libraries have one variant of these types of trees. It's to the extent that when people say binary search trees, they sometimes implicitly mean balanced binary search trees. There are some alternatives to these, which are sometimes simpler and might have some cool additional properties. But given that we've already spent some time on this, I will completely ignore this now. I would love to tell you more about the fancy variants here, but maybe that's for another time. I want to finally show an overview that compares binary search trees and binary heaps. We have here a balanced binary search tree and all the operations that it can support. It's quite a list, right? So we have the get and put, that was the standard symbol table, delete, etc. And then we had the ordered symbol table operations. I put down logarithmic time for min and max because in the way, the easy way you get it, like it's shown in Sedgwick and Wayne's book as well, would give you logarithmic time, but you can tweak it to be constant time by just remembering the minimum and the maximum. That is possible in a binary search tree. But these are the listed times as implementations usually do it, and it's all worst case logarithmic time. And let's briefly compare this to binary heaps again, which have somewhat similar operations. So you can insert things that's similar to put. You can delete the maximum. Well, we can get the maximum and delete. So that's something binary search trees can do. Change key, we don't directly have that, but we can delete and reinsert. And well, maximum, as I said, with some additional twists, you can try to get it in constant time as well. So the question is, if you see this, is there any real point to be made for binary heaps? And why have I shown you this? There's a pedagogical reason, because they're a simple data structure that you can describe in complete detail, but that's beside the point. A second thing is the construction is indeed one difference. You can construct a heap in linear time, but you cannot construct a binary search tree in linear time. The second point is the abstraction of a maximum priority turned out to be useful beyond inspiring binary heaps. As a matter of fact, historically speaking, it came after the fact. People first invented heaps in a very specific context of sorting, and then afterwards figured out this abstract data type that's behind this is actually useful beyond just this application. And it proved useful for many other algorithms, in particular graph algorithms, and one other example that we've seen, that we will see. And finally, this better abstraction inspired people to dig deeper. And after a long sequence of research papers, the final result is that you can support insert and also change key in constant worst case time, with an incredibly complicated data structure that we will definitely not discuss in this class, and I think few people have understood in all detail. But simpler variants, just the Fibonacci heap, get the same thing in amortized time. Somewhat simpler variants exist there that are also practical. So going to the weaker abstract data type that offers only these operations, as opposed to the full range that binary search trees have, allows you to make some of these operations faster than would be possible in the more general model. So having the priority queue abstraction is definitely a big breakthrough in computer science, and therefore discussing heaps and how to implement priority queues is worthwhile doing.